Welcome back. Now we are going to look at the situation where the Lennard-Jones function, or what we call pair potentials, fail. And one of the major criteria is they do not follow the Cauchy's relationship, which says one of the elastic constants C12 has to be equal to C44, and that is one, and also the relaxation is in the wrong direction. So, and that is one of the issues that we want to study a little bit further. So, let us do a VMDL simulation here. So, I am going to show you on your screens this VMDL simulation, which you can look at yourself, called Hook 1, and that essentially will show you relationship on stress and strain, and that is how you will be able to prove to yourself whether C12 is equal to C44 equality is works or not. So, let us start that. Let me first set it up. Okay, stop that. Let us look at averages, get some additional properties, make them bigger. Also, let me get you magnifier. Now we have it. Okay. So, we will start first equilibrate the system. As you can see, in this case it is isothermal because there is a heat bath, and also there is a piston. So, it is also isobaric. So, we are looking at external pressure 0.01, very small pressure, piston mass is 1.0, and you are looking at the number density 0.714, etc., and it has only one green atom. So, let us equilibrate the system, because what we want to do is we want to understand elastic constants. And now, in this case we are going to look at the pressure versus time. So, now you can see there is sinusoidal simple harmonic motion taking place here, and so what we can do here, stress strain curve. So, we can increase the stress. For that, what I want you to do as an experiment on your own is pause it once you equilibrate enough length of time. Then you are 0.01. So, you take a value of 0.02. So, we take small steps. Let us say we go to 0.2 and then run that. So, now I am increasing the stress, and then I am also going to look at the strain. So, you can see that the system went down, is like a spring. So, now we are able to create a stress strain curve. So, you are able to calculate C11 if this is the C11, and similarly you will see that in this case you are restricted to only one force one elastic constant, but by changing configuration of the system you can also measure C12 and C44. So, we will talk about that slightly later, but suffice to say for now, if you do this calculation you will see that Cauchy's equality is not followed in metals. So, that is one of the issues. So, now let us look at some higher pressures. So, for that we are going to stop, pause it, increase the pressure again to 0.5. Now, you can see it further went down. So, what I want you to do with the same temperature, I want you to follow this at least 5 to 10 experimental positions. So, now you can again stop it, pause it, and then put 0.52 to 0.8. Now, let us make observation here, and you have real units are there as well, and you can calculate this particular variation. As you can see here, that there is some tilting of the crystal because you have volume. So, the volume is going to go down as you increase the pressure. So, let us see if we can observe the failure of some of these springs and see if that is possible to achieve. So, we stop here, and then we are going to go another, we went almost 10 times initial value, 1 point something, 1.03, start that. Now, you can see that in the stress strain curve it will start becoming flat because it cannot any further go down. So, and that is where you will see elastic limits is being reached, and if you calculate the stress versus strain by looking at the pressure that you are giving in Pascal and the volume resulting by these two parameters, you are able to calculate C11, C12, C13, etc., C12 and C44, and that is how you establish in your case. If it is a ideal crystal, maybe maybe the Lennard-Jones functions are fine, but if you look at metals where there are lots of electrons, free electrons available or valence electrons, then how do we deal with that, which is what we are going to look at in the next segment. So, now let us look at if we can break this system by going to extremely high pressures. So, I am going to go all the way to 6.29% and see what happens. Now, you saw the piston came down and almost broke the symmetry, and it essentially now it's the entire system is compressed to the minimum, and you can see that there is a sinusoidal curve very clearly indicating here, and it is becoming less and less. So, the system is going into equilibrium position. So, with this stress and the volume gone down, you can now find the stress strain curve. So, this is a good idea with the volume distribution. You can look at kinetic energy, you can look at the energy versus time, you can also look at number density, and as you know, number density will change with the volume change. Most important factor is the pressure for virial, some velocity distributions, and you can also look at concentrations. So, this gives you a very good idea to understand how different system would work in different pressure conditions, and whether metallic system can be modeled by Lennard-Jones, and we know that by semi empirical pair potential metallic systems cannot be modeled, and that is where there was a new technique called embedded atom method potential by Daw and Baskis, two scientists who came up with this model to add some other terms to realistically simulate the behavior of metals, where C12 has to become equal to C44, as well as to understand the behavior of relaxation of the surface when we look at from the molecular dynamics perspective. So, let me stop here, and we will now begin with the many body potential, because atoms do have lots of electronic clouds around that, and that is where it cannot be pair potential, but what we call is many body potentials. Thank you.